for electrical markets and the energy transition. And Professor Ernst is a distinguished professor at the University of Leeds and is a researcher at the Montpellier Institute of Electrical Engineering and Computer Science Research Unit. So Professor Ernst has a very outstanding research achievement, so in terms of publication and also the involvement in the many scientific projects. So because of the time limit, I'm trying to give very briefly the overview about for the second speaker is Professor Arash Moradinejad. So he's from the University of Sussex in the UK, and he is a director of the Smart Vehicle Control Laboratory. And Professor Dijka also has a very outstanding achievement in control and also application to the vehicle. And today he is going to address his talk about the energy management strategies. So my journey from vehicles. So based on these two presentations, I would like to mention that our journal also publishes frequently the papers in the energy context. So you can find as a three representative of the publication on this page has been already published in the complex engineering system, and you are very welcome to look at these three publications to find out more new topics already addressed in this. To give the floor to the first speaker, so Professor Ernst. So if you are ready, so Daniel, the floor is yours, and please you can start.
Yes, okay. Okay, thanks a lot. So I will take control over the screen. Can you hear me well? Yes?
Yes.
No problem. Yes, okay. I will share the screen. How long do I have for talking, Mr. Chairman?
It would be great if you could manage in 25 minutes. Okay.
Okay, 25 minutes would be okay. Let me share, go in slideshow mode. Is it okay like this? You can see the screen pretty well, yes? Okay.
Yes, that's right.
So it's 4:06, past 2. I will try to finish at 2:30. Okay, I'm going to talk a little bit about reinforcement learning for electrical markets and the energy transition. It's a summary of the works I have carried out with my many collaborators over these last, I would say, 5 or 6 years. Well, there are very few people in artificial intelligence, robotics, who know a little bit about how electricity markets work. I should you one in your life once follow a class about electrical markets. I mean, during the first class, they will display you this figure here on the screen. So you have generation companies. They sell electricity through what we call a wholesale market to large consumers or through small consumers through retailers. So that's the dominant model for electricity markets, and this model has been implemented all over in Europe. What you need to know is that when you sell electricity to someone, you actually sell a quantity of electrical energy related to a specific market period. It can be either 15 minutes or 30 minutes in Europe. So when you buy electricity, really what you buy, it's a quantity related to a market period. And electricity markets, well, these are like complex games because you do not have one market where you buy or sell electricity. You have several markets, and you have markets related to future products. Okay. For example, for let's say one specific market period, let's say now between 2 p.m. and a 2:15, you can already buy the electricity 6 years in advance on this forward market. Usually in this forward market, you do not buy electricity for a single market period, but let's say electricity for all the market periods covering 1 month, 1 quarter, or 1 year. And then the closer you move to the real time, let's say the delivery time, the more the granularity of the market is increasing. You have the so-called and well-known day-ahead markets. That's a market where you buy on the day ahead electricity for the next day. You have around 35% to 40%, of the volumes that go to this market. And then you have the intraday market. And finally, you have also after the delivery or just before the delivery, the balancing market, the ancillary market. So it's a difficult game. It's a difficult game playing with these markets. And the prices may vary a lot. And that's one specificity of electricity markets is that the price related to a market period, let's say at noon, can be pretty much different from the price that you pay in the evening. And here you have an example. That's the picture that dates from 2021 of the price of electricity for different forward products. For the month of December, it would cost you 177 euros per megawatt hour. And you see that, for example, for February, it would be more expensive. These are the monthly products. At the bottom of the slide, you can see the forward product for different years. You see that in 2021, you wouldn't pay much, for the electricity. In 2024, 67 euros per megawatt hour, while it would be 115 euros per megawatt hour for 2022. This gives you an idea about the number. Okay, but let us go to the main point of this talk. It's the use of reinforcement learning for interacting with electricity market. So what is reinforcement learning? So reinforcement learning, it really refers, these are well-known machine learning techniques. It refers, let's say, to techniques, that enable one to solve a complex, stochastic, sequential, optimal decision-making problem. And this is important from the information generated through interaction with the system. So basically, you have a problem, a complex optimal sequential decision-making problem. You interact with the problem. So you take decision, you observe the effect of the decisions on the system. You generate what we call trajectories. And from these trajectories, you basically try to infer a control policy that will maximize a sum of rewards. Okay. The main three reasons why reinforcement learning techniques are extremely promising for solving let's say, market problems is that first, these techniques, they really seek to maximize a numerical reward signal. And it's exactly what you want to do when you play with markets, any type of market, because you want to maximize the amount of money that you make when interacting with those markets. So you have this reward signal which is defined. That's not always the case. For example, suppose that you use reinforcement learning techniques for robotics. I mean, the reward signals is not that immediate to find. The reward signal should, in some sense, in robotics, represent how well the robots behave, and that may be more difficult to define. You have also, and that's extremely important, a sequential nature in the decision that you take when you interact with electricity market. And this sequential nature has two sources. First source is that you have a sequence of markets to which is associated a sequence of decision, like what you need to buy and sell in every of those markets. And then you have also many devices that participate to the time coupling of the decisions. I'm talking about mostly the batteries. If you decide to discharge a battery to a market period, I mean, you won't be able to discharge perhaps it at the next market period. So there you get a time coupling between the decision. So this is another reason, this time coupling between the decision. This is a reason why reinforcement learning techniques are also very, very promising for interacting with the electricity market. And thirdly, these problems are extremely stochastic. And when you interact with market, they are stochastic, and it's difficult, to model the environment. And that's also a third reason why reinforcement learning techniques are extremely promising, because these are techniques that are well suited for dealing with stochastic system. Okay. And I'm working 4 years now on the design, let's say, of very good reinforcement learning agent that are able to interact simultaneously with the different type of market, with all these markets at once. That's an ambitious result. So I'm going to present you, because we do not have a lot of time, I'm going to present you shortly the results that we have had by dealing with one specific type of market, the so-called intraday markets. I want to emphasize that this work has been published in one of the best machine learning paper, machine learning, that's the name of one of the best machine learning journal, machine learning. So it's very rare to have applications published in those top journals, and we are very proud of this work. And it's a work that we have carried out with the NG Trading Group. That's probably one of the best trading group in the world, and they are using advanced machine learning techniques for their trading. So this represents a little bit how an intraday market work. Okay, you can start dealing, at 4 p.m. the day before, the 4 p.m. products, for the next day. The next day starts at midnight and it finishes at midnight, and you have products that are related to every quarter of the next day. And half an hour before the beginning, of a market period, you cannot trade product for the market period. So let's say that the first product that you can trade is between midnight and a quarter past midnight. At 11:30 p.m., you cannot trade this product. It's why you have for the first product Q1. Okay, there is the time of closure for the trading of this product. Okay. And here is typically an order book. You have an order book for this market, an order book related to every product. You have 96 products for this market, 4 products per hour, 24 hours a day, 4 multiplied by 24, 96. And for every product, you always see the same, a quantity, okay, and a price. Either it's a product for which you sell, it's a sell product, okay, you are ready here in the example to sell 4.25 megawatt hour of power at a price of 36.3, or you are ready to buy, okay, you put bits for buying electricity at a price here, for example, 3.8 euros per megawatt hour and a quantity of 3.15 megawatt. Right? That's how it works. And we have used reinforcement learning techniques for using this. The generic reinforcement learning scheme is the following. You have a reinforcement learning agent, you take an action, you apply the action on the environment, and you get a state reward as outcome, a reward as outcome, and also an observation of the state or partial information of the state. In this context, we have considered an interaction with the intraday market where you have a battery. So you can interact with the intraday market, and you can also control the battery. So really the entity that controls the battery, and determines, what are the bits it should grab on the day-rate market. These are the 2 actions that it can take. It can observe, as observation, it can observe the state of the battery and many things about the markets, mostly information related to the order book. And the reward is naturally the money it makes during each market period. I won't go through the details here, But when you deal with reinforcement learning problem, you need to define what is the state space, how do you represent the state, what are the features you extract from the state, what is the action space, the type of environment you are really dealing with, adversarial, non-adversarial, fully observable, partially observable, and so on, so on. For this example, we have used the well-known algorithm. It's a batch mode reinforcement learning algorithm. So it exploits at once a set of trajectories by learning what we call a sequence of state action value function. We have used this algorithm with deep neural nets as function approximators, and in particular, deep neural nets made from LSTM neurons, several layers of fully connected neurons like this. And we have tested, the policy use against a policy that was usually used by trader. And for example, here is the rich return that we make per day, okay, the value, the money that we generate. So 667 euros per day, okay, versus, with already a good policy, but that does not rely on artificial intelligence, 645 euros per day. So again, in between 3 and 4%. That's typically, I mean, we have worked a lot with traders. That's typically the additional money that you can earn, by using advanced trading techniques. It's significant, 4% more, with respect to the already very good techniques that they have for now. Okay, that's one application for us of reinforcement learning to, let's say, trading activity. We have worked on other application. I won't detail all the other application, but one of those other applications is the renewable energy communities. So what are renewable energy communities? That's a concept which is pretty new in Europe. It has been introduced, in the EU legislation, I would say 5 years ago. And it's basically, a set of consumers that can or produce or that can bypass, the wholesale market, and trade electricity directly between them, between the member of the communities. So this trading is difficult to do, especially when you have, the community that owns also flexible devices like batteries. You rapidly have to face difficult sequential decision-making problems. So we have observed, I just want to emphasize this application, which is important. We have generated very interesting results by relying on those techniques, those reinforcement learning techniques. I won't enter into the details, but I can point to the paper which is given on this slide. Other successes that we have had using these reinforcement learning techniques is for the sizings of complex energy systems. Now, energy systems change rapidly because of renewables, because of new types of loads, EVs, heat pumps, and so on, so on. And it's very difficult, for investors to know exactly the type of investment that they should do. And we have formalized those problems, and we have found out that the investment that they need to do can be formalized as a kind of a two-stage, optimal decision-making problem, where in the first stage you make the investment, and in the second stage, you control the system. So you are basically optimizing at the same time the environment. Okay, that would be a reinforcement learning problem, where you are at the same time optimizing the environment and the control policies, a paradigm in reinforcement learning that has been very little studied, and that should probably receive much more application. So that would be the paradigm. You would have on the left the classical reinforcement learning scheme, And here on the right, a design agent, that interact with these schemes for optimizing what we call the dynamics of the system. Here is one algorithm, okay? Again, I won't enter into the details. Everything is in the paper. One algorithm that we have proposed for handling those problems. I give you an example. Suppose that you have here on the right the microgrid. It's a microgrid where you have a load, you have PV panel, diesel generators, batteries. What is, the best investment that you should make? How many PV panels should you install? What would be the power of the diesel generator? What would be the size of the batteries, to lead to a system that minimizes costs, for providing enough electricity to the load? We have tested our new approach, on this system, and we see it's the blue curve on the figure that we have outperformed, an existing algorithm called JODC on this problem. And I like this because it shows you that the research, I like this slide because it shows you that the research done at a very good level, using artificial intelligence technique, for tackling, specific problems related to energy can also be used to other fields. Okay, so we have used exactly the same algorithm as the one shown before, but here for sizing, let's say for designing a drone. So we had a drone, we had to design a drone so that it could at best, follow the green trajectory on the bottom left. Okay, and we have used exactly the same algorithm, and with some successes, we have been able to find what was the best design for this drone. So here you see going from let's say energy related problem, we could have impacts also on classical problems related to robotics. And again, there is a reference in the talk to the papers published in Journal of Artificial Intelligence Research that details this. I won't be much longer. I just would like to say that the electrical grid, a few years ago, was made of on the transmission network to which were connected distribution network, and the electricity was flowing from transmission the network to distribution network, and you didn't have any, let's say, advanced control schemes at the distribution level. But now the grid is fully changing. Atop of the transmission network, you have huge HVDC links that have been created, built, then these HVDC links, they need, advanced control strategies. You need more advanced control strategies for the transmission network, and also advanced control strategy for the distribution networks, also called the active network management schemes. So in a few years, you are moving, from a two-layer system with one active control layer to a three-layer system where you need advanced control schemes for the three layers, and that raises a lot of challenges. Sadly, you have very few people from, let's say, artificial intelligence who really work. They love to work on problems related to robotics, large language models, all those problems, but very few of them work with problems related to energy system, and that's probably because there is a lack of good benchmarks in this field that they can easily use, for testing these algorithms. And in an effort, to try to overcome this problem, we have designed, let's say, a gym environment, a well-known gym environment, and this environment has been developed by OpenAI for, testing algorithms on let's say, electrical systems. And these environments, they are made available, and you can download them on my website or on a GitHub. I'm just finishing this talk by giving you a demonstration of this environmental control scheme. Here you have a system. You can control when to charge, discharge the batteries, when you curtail generation so as to avoid congestion, voltage problems on the power systems. And if you look at the presentation, you can play the video and you can see how these systems can be adequately controlled by reinforcement learning algorithms, and you can reuse all the graphic interface, all these environments for testing your favorite algorithm on this electrical system. Something I would appreciate a lot, because I think it's very, very important that more people in artificial intelligence work on those classes of problems. I would like to thank you a lot for your attention, and I think I haven't been too long.
Thank you very much, uh, Damien, for being in time for your presentation. So if you agree, I would like to ask you, please stay with us, because based on the plan, after the second speech, we opened the panel discussion. And then after the second speech has been done, perhaps there could be some questions from the audiences for your talk. Would you like to answer the question, or
No, we can wait for the second speech.
okay?
Okay.
Okay, thank you very much for address this very interesting and outstanding presentation. Now it's time for the second speech is given by Professor Moradinejad Dishka from University of Sussex. So the Arash floor is yours. You can start when you're ready.
Yeah, thank you, Hamid. Thank you, Damien, for a very good presentation. My name is Arash from University of Sussex in the UK, in the very south of UK in Brighton. And my presentation today is about generally energy efficient control algorithms. And instead of focusing on the details of techniques, I would love to actually tell you a story, my story and my students' story during the past 10 years, that what we have done and what problems we try to solve, and maybe it can be useful for the audience. So if I want to give you the keywords of my research, I would say that energy efficiency is one of the major keywords, but I'm focusing on developing algorithms and control strategies considering this energy efficiency. And as a result, I would say that I'm working on efficient control algorithms. Applications, normally it's in a bit different applications, from renewable energy to vehicles, electrified vehicles, and also robots. So I would say that if I want to summarize my interest in research, I would say that novel energy efficient planning and control algorithms for different applications. So one of the keywords that thankfully Damien also mentioned, I just want to clarify it here, is energy management strategy. Actually, energy management strategy specifies a control problem of optimally managing energy flows with respect to, within a system, with respect to one or more constraints, to make sure that the energy demand is always met. But when we say energy efficient control strategies, normally we consider minimization of energy consumption, but as the secondary objective, means that we always want to meet the energy requirement, but meanwhile we want to minimize the energy consumption as well. Another keyword which is related here is the control allocation algorithm or problems, because most of the time these systems are called over actuated systems, means that you can you can meet the energy consumption or energy requirement with different ways, and in most cases with infinite ways. Then the question is that which one is the best with respect to the secondary objective. And these kind of problems are normally called control allocation problems. So as I said, it's a kind of case study by case study. I'm introducing you a few case studies which are related to the concepts that I mentioned. One case study is an energy management strategy for standalone renewable, hybrid renewable energy systems. A standalone means that it's not connected to the grid. So these are small renewable energy sites, normally in remote areas, not connected to the grid. And also, when we say hybrid renewable energy systems, means that it has more than one type of renewable energy source, like wind turbine and solar panels together, or it could be different types. So not being connected to the network actually makes it a bit more complex and challenging from the control perspective, because the grid is actually can be assumed actually as a infinite capacity battery which is connected to your system, but without having it, actually all your capacities are, and particularly storage capacity is limited. Then the question is that how you can stabilize such a DC microgrid in a way that you can make sure that here, for example, this is a DC bus, the voltage of this DC bus is always within a range, and it means that you're managing the consumption and the production of energy, and also how you can share the power demand proportionally in a very, let's say, in a fair way between different sources of energy. And in another very important thing that we focus in this research was that when you have limited battery, the charging regime of that battery is very critical, because if you don't charge it properly, the batteries would be damaged very, very easily. And particularly when you don't have grid, here it means that you should be able to curtail or the production whenever it's required, in a way that you make sure that the batteries are charged properly. So we formulated such a problem as an optimal control problem, and then it has some challenges. Next slide I will show you. And then we develop a non-linear model predictive controller to solve it successfully. So the challenges of such a system is that, first of all, of course, it's non-linear system, but more than being non-linear is that at least two components of such a system are discontinuous, means that their operation changes completely with respect to some other events in the system. Means that, for example, battery is one of those discontinuous systems. The behavior of battery when it's charged is completely different from its behavior when it's discharged. Electric motor is another one, because its behavior when it's is doing the motoring is different from its behavior when it's doing generation. So these are main challenges of such a system, and then it lays two main issues to solve such a problem numerically. One is that, first of all, formulating such a problem is a bit difficult. And second is that formulating in a way that you can solve it with available tool sets is another problem. So actually, I don't want to go to the details. I just want to tell you the main approaches that we use that may be useful for the audience for their problem as well. First of all, we focus on a mathematical technique called complementarity constraints. And complementary constraints is very good to model the discontinuities. The good thing about complementarity constraints is that we have numerical tools to solve complementarity constraints. So in other words, we convert the problem of a discontinuous system to a problem with complementarity constraints that thankfully we can solve it numerically as well. So this is one way that we did. Complementarity constraints actually is shown in this equation. Actually, this is a symbol of it, but meaning is that at any time, either of the sides of the symbol would be in its boundaries. Means that at any point, either, for example, gamma 1 of gamma 1 is actually equals I battery stack, or gamma 1 is either 1 or 0. So every time that you get a sample, either of these conditions would happen. Then we use Modelica, and Modelica is a very good language, modeling language for modeling a system using directly the mathematical equations. And then there are tools that can compile Modelica language equations, but we use an open Modelica, which is open source tool as well. So why is important? Because Modelica actually, with Modelica, you can validate and evaluate your developed model directly by using the developed equations. You can't do it easily in MATLAB, for example, or in Simulink, but in Modelica, you can do it, and it's designed for such a purpose. So as you can see here, we've given the equations of such a hybrid renewable energy system directly, and this is a model of that system. And then you can simulate and make sure that those equations work well and they are stable. And then you can use those equations for the development of your controller. Another technique or another tool that we use was to solve the developed optimal control problem, that we use a tool called CASADI, which is developed in Belgium, where Damian is from, in the University of KU Leuven. And this is a very effective tool to formulate and solve the nonlinear MPC problems that we have used. But the point is that because the system is just discontinuous, that makes that solver a bit more complex in a way that you should make the sampling time variable over the time. So you can't have a fixed sampling time. So you should make the variable sampling time in order to find out the location of those discontinuities. So as a result, we solve it, and you can see that here the variation of the resources, wind and solar, and also torque demand, load demand, but still you can see that the voltage of the DC bus keeps constant within a range. And also by doing the curtailment, here you can see of the solar and the wind branch, the charging of the battery is with the constant current, with a increasingly current, slightly increased current, but at the constant voltage. And it helps to charge a battery for a larger SOC without damaging the battery. And it was the main purpose of this algorithm. Then we focus on another problem. The problem was on energy management strategy of electrified vehicles. In this case, it was a fully electric vehicles, but with multiple drivetrain. So it means that this car has 4 electric vehicles, 1 per each wheel. Then the question was that how we can manage, or how we can use these multiple electric vehicles, electric motors, in a way that we can reduce the energy consumption, or in other words, with minimizing the energy consumption. Or in other words, that if having multiple electric motors can reduce the energy consumption of an electric vehicle or not. And we showed that yes, it can be. We formulated the problem. I'm not focusing on the detail, but again, this problem has the same issue that electric motors can be either working generator or motoring, and it should switch between them and cannot work at the same operation. And then the question is that when this should be switched off. The point is that we showed that such a problem can be solved for each side of the electric vehicles. So we simplified the problem. Then we also showed that, mathematically proved that the optimum solution cannot be a mix of each side, cannot be a mix of traction and generation. So the optimal solution of each side is either generation or traction. And this solved the problem. This made the problem very straightforward and simplified in a way that we converted the optimization problem to algebraic problem. We showed that the optimal solution of each side is either single traction, means using just one of the motors, or even distribution, means using them equally. And then the question would be that when we should switch between them, that we formulated an algebraic equation that its solution tells us the torque of the switching. So by increasing the torque, there is a specific point, depending on the speed, that you should switch between even and single axle solution. So then we actually used the system that we had for deriving the power loss curves of the vehicle at each speed of the vehicle. We fit it to that power loss curves that the algebraic equation uses it, and then we solved it for each of the speeds of the car, and we found a switching torque for each speed. And as a result, the final solution was very simple, a simple lookup table that tells us that what should be the switching point of the torque of each side of the vehicle, depending on the speed of the vehicle. And putting it in the ECU of the vehicle, actually we showed that we can have up to 4%, up to 4.6% of energy reduction, depending on the driving cycle, test cycles of the vehicles. The third problem that we attacked was that if any look ahead information from the road can help us to improve or reduce the pollution of the engines. So it means that if I have a camera, as you can see here, that can see a part of the road ahead of the vehicle and use that information to improve the control of this engine, would it have any effect on the efficiency of the engine in terms of particularly its pollution? Can we reduce the pollution of such an engine? And if yes, then how long of this look ahead information is effective? And finally, is that what is the technique we can use to exploit those look ahead information for controlling the engine? We answered all those questions. Actually, first of all, we did extensive statistical research, finding that about 2 seconds of look ahead information is enough, and particularly in the form of torque demand. So if we know torque demand of that our vehicle would experience within the next 2 seconds, it's effective, and we don't need to have more look ahead information. We did it, for example, by extensive autocorrelation and cross correlation analysis, some statistical terms, methods, and so on. And then we use the 2-layer economic MPC technique. Economic MPC, economic model predictive control, unlike the general model predictive control, doesn't track the optimal solution, but by itself finds the equilibrium point as well. So it's called economic because it doesn't know what is the equilibrium point or optimal solution that it tracks. It finds it and tracks it both together. And then the result of it was controlling the turbocharger and the 2 EGR of a vehicle, that this vehicle was in production line on JLR. And we showed, based on our hardware in the loop simulation, that such a technique of look ahead information, exploiting look ahead information, can reduce the NOx by 9% and soot by 14%, as compared to the optimal controller without having that look ahead information. So this 9% and 14% is just the effect of look at, as considering the data in future. And it's good to know. It's good to note that the NOx and soot are contradictory. There is a trade-off between them, and improving NOx normally decreasing soot. Improving NOx degrading actually the soot emission. But we could find, by developing such an algorithm, we could find the optimal solution that the car manufacturer and the engine developers couldn't find it before. Because generally the technique that they use in car manufacturing, car industry, is that they do a lot of extensive tests and practical tests. However, not blind, but it has lots of theories behind, in order to find the solutions as lookup tables and put that lookup tables in the ECU of the car. But we showed that the extensive work that they had done was not able to find this optimal solution, that our system could find it. And as a result, we could show that this is such a significant reduction in the NOx. And so this result has been patented as well in the UK. Then we came up with another problem. So as you can see, all about energy consumption and energy efficiency or pollution efficiency, but in different applications. Then we came across another question, research question, which is related to energy efficiency, but for connected and autonomous vehicles. That the question is that if having all the cars connected and autonomous vehicles, can we improve the throughput of intersections, and how it can be, or can we formulate such a problem and then solve it and show that the throughput of the intersection, having all the vehicles collaborative and autonomous, would improve the throughput. So we formulated again such a problem as the optimal control problem, and with some difficulties we solved it. And you can see the results here, for example, as a solution of such a algorithm, that how the vehicles would cross such an intersection if they are fully autonomous. For example, this is one case study. Next is a bit more complex case study. And yeah, so as you can see, the vehicles actually cross in a lane free and signal free, and we showed that using such a technique can improve the throughput of the intersection by about the percentage I can't remember. I can calculate now. Yeah, it's about 80%. And however, this is for a this is a benchmark that we showed that this value of the throughput is actually limited by the by the theories of the geometry. So this and our technique could reach to that theory, that limit of the geometry, and we showed that we can use the results of such algorithm as a benchmark for any such algorithm that wants to control the signals of the intersection or controlling the vehicles. And finally, the last question that we came across was about in robotics. The question is interesting. It's within a class of problems called informative path planning. And the question is that if we can efficiently and in an energy efficient way control or plan the path of a robot with a single uncertain sensor to make a map of a completely unknown area. So in other words, is that we want to make a map of a completely unknown area. Then the question is that if without having anything about that map, we can find a close to the global optimal solution of such a problem. And we showed that our algorithm actually could find it as the solution, and then we find a benchmark for it. We compared and we showed that it works properly, making a map, ignoring the left-hand side. This is just the RRT star for obstacle avoidance, but these red points are the paths, and this bottom left is the most confident map that it generates. And then the question, this is the outcome of our algorithm. Then the next question was that, okay, can we benchmark it? So how we can compare the outcome of such algorithm, saying that this algorithm works properly or not properly. And then we defined a posterior problem, means that we assume that we know the map and we want to remap it. And finding the solution of such a posterior problem, which is a remapping of a known map, we assume it as a benchmark, and we showed that our algorithm follows the benchmark here, as you can see, which is a linear behavior of number of identified cells over the traveling time. So it shows that how linearly the number of identified cells increases. And our algorithm actually follows that trend of the posterior of the benchmark solution over a very good range of the time, up to about 60% of the time, before reaching to a kind of saturation, that it just moves a lot, but just for one cell or another cell. So I just want to finish my talk with one point, that when we want to test these algorithms that I mentioned, we reach to the point that we need a tool, and we develop a tool. We call it ROBIL, Robot in the Loop Simulator, that actually is the tool to test the collaborative or distributed algorithms. When you have multiple of robots, multiple of cars, and your algorithm should run on multiple of them, then it's a very expensive to test your algorithm in reality. Then the question is that if we can use the scaled down robots, for example, in case of cars, to do the middle test of such algorithms in a very cost-effective way. And we developed the ROBIL based on a technology called ROS, Robotic Operating System, and it's on top of it in a way that you develop your robot in a SolidWorks integrated into it, and then you use either this SolidWorks model as a digital twin of your real robot, or you use the real robot or a combination of them to test your algorithm. That this video shows the results, and this is a video of that algorithm for crossing the intersection that I explained before. That the bottom ones are the results of generated by MATLAB, And the top ones are the ones generated by Robil, but one in the top left using the real robot, top right using the digital twin of it. So using this tool, we are testing the performance of our algorithms in a actually close to real situation for different algorithms that we have. Thank you very much for your time and your attention. Sorry, I think I was a couple of minutes later than expected.
Thank you very much, Arash, for this excellent presentation. Now is the time for the panel discussion. So perhaps the audiences or the participants in this webinar could raise the hand and ask the question to our two speakers. So are there any questions from the participants? So either you can direct the talk in this meeting room, or you can drop your question in the chat box, and then I can read it and we can try to get the answer from the speakers. So of course, these two presentations today, so they are addressing one of the key points. So how the AI technology can be applicable to the application, either robotics or to the energy systems. And the first presentation by Professor Damian Ernst. So it's quite important from the energy market. So, Daniel, I have one curiosity to better understand from my knowledge. So, the one issue we have in the energy sector is the companies, because there are a lot of investors. There are a lot of basically the company they want to invest in this kind of the business. So now the point is that if the AI or the reinforcement learning, they bring some solutions. So basically for the energy, the trans sectors. So how the companies or how challenges the industry or the company will face to implement. So this kind of the technology is coming out of, or the solution coming out of the AI or the reinforcement learning. So I'm asking you from the industry side. So what kind of challenges they face? Okay.
Well, it's difficult for them. Honestly, it's difficult for them. Why? Because they face, well, in every sector, let's say the decision-making problem that you face are very specific. In robotics, they are specific. Autonomous car driving, they are specific. If you want to, I don't know, control rockets, it's specific. And they are specific. So it's very, very rare that they can use off-the-shelf, artificial intelligence techniques for really making breakthrough in their field. They need to develop customized techniques. And for developing customized techniques, you need to have high-level people. Only high-level people are able to do it. And there is a kind of competition for talents between this industry and I would say the software industry, all these big AI giants, Microsoft, Google's, NVIDIA, and so on, so on. And sometimes, they do not offer salaries, which are big enough, to compete in terms of salaries, although also for attracting these giants. So, in summary, it says for consequences that they have difficulties, to have the staff, required really for transforming their companies and tapping a lot on AI for improving the efficiency of their businesses. So this is one of the problem they face. Yes.
Okay, thank you. So, but Arash, I think you presented a very interesting case studies in your presentation. So, of course, you talk about some sort of the energy management EMS for the single car or the single agent. And because I want to find some similarity to the first speech, because you try to look at the torque management. So basically for the vehicle, and you try to see how to distribute the torque between the different the motors part. It means this is one of the cases we discussed. So in this context, because the Damien, he also presented about the AI, how to leverage the AI or the reinforcement learning for this kind of the energy, the distribution, so between the in some applications like a smart grid. So my point is that how do you think that how the some techniques like the AI or the reinforcement learning so could give a benefits to, for example, to one of the cases like case one you mentioned. So what do you think about this kind of the technologies?
Yeah, I think it's a it's a challenging question, but it is my understanding. I would say that generally we have a problem that is formulated as an optimal control problem. This is a common problem between reinforcement learning and also, for example, model predictive control. So the common problem is that we have an optimal control problem, and the definition means that you have an optimization problem that has dynamics involved as well. And dynamics, in very simple words, are differential equations. Then it's shown that in order to solving it in most cases is not straightforward, then we approximate the solution of it. And model predictive control is a technique, is one of the techniques to approximate the solution. And reinforcement learning is another technique for approximating its solution. They have lots of similarities, but a major focus of model predictive control is that you have a model or you can have a good model of the system, but when you don't have a model, instead you have lots of data, then of course AI techniques are very effective. My experience is that for small systems that we are focusing, as you mentioned, standalone technique systems, in most cases we can have a model or a good model, or but not necessarily, we don't necessarily have an established system to be able to get lots of data out of it. So in that cases, I think model predictive control is effective, which is based on the numerical solutions. But now we are working, for example, in our team on data-driven techniques as well, direct data-driven techniques as well, either reinforcement learning or Koopman-based, to use directly the data instead of having a model of the systems. So I don't have a very clear answer to your question, but this is my understanding of the situation.
Yes, thank you very much. I think it's very clear to me. So, Damien, there is one question I think is related to your talk from the participant. So he's asking you what kind of tools you are using for simulation of the complex engineering system. So maybe if you have
Yeah.
some ideas
Yeah.
or something.
Yes, for the distribution grids, so the active network management grids, active network management schemes, we are using our own GIM simulator called GIM benchmark. So it's freely available, so they can use it. They can send me an email or access to the presentation, and there will be a link to the simulators. For the markets, I mean, these are our own simulators, okay? Because you need for building these simulators, you need to have an history of the order books of the market, and we cannot make them publicly available. That's not possible. And let's say for the small problems about both sizing, so designing the environment and controlling it, all the benchmarks are freely available on GitHub. They need to go to the corresponding paper, and they will find a link to GitHub, or they can send me directly an email for additional information.
Okay, thank you very much, because I think the participant got the answer they did you. So I hope that the answer is sufficient. If not, maybe you could contact Professor Damian by email. So because of the time, so first thing that this webinar is live stream on the YouTube. I think later on you can get a link on the YouTube to find your speech. So because this is the one basically the part for the journal already created on the YouTube channel. Okay, so based on the presentation today, so I would like to thank Professor Evans for his excellent presentation, and also Professor Muradin Nejad for giving a very informative presentation about EMS. So I would like to again thanks all of you, especially our distinguished speakers and also the participants for attending these webinars. As I mentioned before, so we are frequently organizing the webinar through the Journal of Complex Engineering Systems, and I would be happy to meet you again in the future webinars. And please also consider to submit your contribution to the journal. So at the end, thank you very much. I have no other point. Then just thank you again. Have a nice day and take care. And looking forward to meet you again in the future. Thank you.
Thank you.
Thank you. Thank you.
Okay, thank you.
Thank
Bye
you.
bye. Bye. Okay,
Thank you
thank you,
for your
Lyric.
presentation.
Thank you.
Thank you, Damien and
Yeah.
Hamid and Arash. Thank you, all of our attendees. Yeah, thank you for
Okay.
attending our webinar, and we can keep in touch later, and say if we could have a deeper cooperation or collaboration with each other. Yes, we really hope
Okay.
to keep in touch with you, and we hope to have further cooperations. Yes,
Thanks a lot.
Oh, thank
thank
you.
you so
Sure.
much.
Thank you.
Yeah, thank you for
Thank
your
you.
efforts.
Okay, and also Damien and Arash, welcome to visit us at Politecnico Milano anytime. So then hope to meet you in
Promise.
person in the future. Thank you. Bye bye.
Promise.
Yeah.
Next
Thank
time
you
I
very
come
much.
to Italy, I will visit you.
Yes.
Thanks. Bye.
Thank
you.
you. Bye
Bye-bye.
bye.
Thank you. Thank you. Bye bye. Bye bye. Bye bye.
Bye bye. Bye bye.
Bye-bye.